Hello guys, today we are going to start with the most important topic in chemistry for this session. The topic is isomerism. Well, it does not form a whole chapter as such, but if we go to see, isomerism plays a very important role in predicting the stability of a particular molecule. What do you actually mean by it? Isomerism, if we go to define, is the phenomenon by which a particular molecule is going to exist in its most stable form. Lesser the energy of a particular molecule, more will be the stability. This is what we have been studying for quite a number of years. So let us see as to if at all a molecule is giving us a particular state of itself, that is, with a particular functional group attached at a specific position in its structure, why it is going to be called as a product or why it is going to be called as a more stable form of that particular molecule. Now, before that, I need to tell you as to what do you mean by isomerism or what do you mean by an isomer. Isomerism is a phenomenon by which a molecule exists in its most stable state with the same molecular formula but a different structural formula. Well, this comes down to the main term, that is isomers. Isomers are defined as the molecules, okay, two same molecules or either ways two different molecules wherein their molecular formula will be the same one. What do you mean by molecular formula? It's that condensed formula which gives us the number of carbon atoms, number of hydrogen atoms and number of any kind of heteroatom present in a particular structure. But they will be having some different structural formulas. Now, let us draw the structure of hexanol. You would be asking as to which hexanol are we drawing? Is it one hexanol? Is it two? Or is it three? It's going to differ as per the names. It is going to differ as to where is the OH group going to be attached. So let us draw the diagram or draw the structure. So here we go to draw. So over here, as we see, in this structure, we are having the attachment of OH group on the very first carbon atom. In this case, if I go to count, I'm having second and third carbon atom over here itself on the fourth one, okay. From here, if I go to count, it's 1, 2, 3, 4, 5, okay. Now, of course, we know one thing is that whenever we go to count the number of carbon atoms, we count the one which is, the lowest number will be given or assigned to that particular carbon atom, which will be giving us the lowest number to the substituent or to the principal functional group. So in that case, of course, we are going to count from here in this case. So 1, 2, in this case, it would be 1, 2, 3, okay. And in the other case, it's on the very first carbon atom, fine. So this is going to give me one hexanol. The other one is going to give me 3 hexanol. And this one is going to give me 2 hexanol. Irrespective of the names in each of the cases, the molecular formula still remains the same. 1, 2, 3, 4, 5, 6. 6 carbon atoms. 3 plus 1, 4, 5, 7, 9, 11 and 14 and 1 O. Same happens in this case. Same happens in this case. So this means all of these are isomers. Isomers meaning to say that they are having the same molecular formula but different structural formula. So this is a very small example as to what do you as to explain as to what do you mean by isomerism or what do you mean by isomers. What we'll be doing is, we will be advancing towards the classification of isomerism on a very large scale basis. So let us do that. Let us just classify as to what do you have or what do you have as the branches of isomerism. So just let's pen down under the main heading of isomerism, which is divided into two sections. Okay, the first one will be structural, under which I have many categories. So let us have a look as to which are all the categories. Under structural isomerism, one is called as the chain isomerism. I'm just giving the pre-headings of it. I'm not following them with the suffix as isomerism. That's quite understood. So chain isomerism, then we are having ring chain. One more form of isomerism is tautomerism. The other one is called as functional isomerism. The next one is positional. And the other one is metamerism. Okay. Now, before going on to the second branch, I need to explain as to what we have over here. Structural isomerism, as we have seen, is the the very first category under isomerism, and under that we are having 6 more branches, giving it as chain, ring chain, tautomerism, functional, positional, and metamerism. Now, to have just a gist of it as to what do you mean each of these terms, we'll just have one line definition for each of them. Of course, by chain you mean that it will be having the same chain length, okay? But in this case, if you go to see, you can have the attachment of many kind of alkyl groups in different positions. Yes, of course, we'll be dealing with examples once again, but to get a gist of it, let us just go through the line definitions. In the case of ring chain isomerism, you can say that one of them will be an open chain while the other one would be a cyclic chain. Of course, again, we will be having the same structural formula, okay? In case of tautomerism, you will be having some different kind of isomerism existing over here. Now, this actually is seen in some of the majority of organic reactions wherein a molecule undergoes interconversion. Okay. Now, interconversion of course means that it would be due to the simultaneous shift of some kind of bonds or some kind of atoms. Which of them are bonds and which of them are atoms will be going on with the specific example. The next one comes out to be a functional isomerism. Now, in this case, we'll be having some different functional groups being placed at different positions in 2 molecules or more than 2 molecules. In case of positional isomerism, we'll be having the placing of functional groups, or other ways you could say it's the placing of multiple bonds in a particular molecule at different positions. And metamerism is a very, very, very rare case which comes out to be in case of any kind of organic molecules. So in case of metamerism, you can say that it is the different positions of polyvalency functional groups which will be differing in their positions on a particular molecule. Okay, so 6 types of sub-branches, and we'll be getting on to much more examples to have a detailed view of this. Yes, now let's start with the various branches of structural isomerism. Okay, now as in the last session we have already done with the one-line definitions for each of them, right? So we were having almost 6 categories, okay? Chain, positional, functional, ring chain, metamerism, and of course we cannot miss out with tautomerism, which is going to be the isomerism which is seen in kind of various reactions, okay? Now let us take some specific examples so that we can have a whole idea as to what do you mean by these one-line definitions. So for chain isomerism, I go to take an example of the simplest hydrocarbon, that is your butane. Okay. Of course, butane is known to us with 4 carbon atoms, right? So the general formula goes in as CnH2n plus 2. So accordingly, we will be having it as C4H10. Okay. So that is your molecular formula. Now in this case, if we go to draw a straight chain, these are the 4 carbon atoms, and accordingly, I place the hydrogen atoms to fulfill the tetravalency. Okay. Now this can of course be represented by some other way also. That would be like this. Now, if you remember, we have studied these concepts in our basic principles also. So over here, you can name this particular chain, the very first molecule, as N-butane, and this is your isobutane. Isobutane is the attachment of your methyl group on the second carbon atom, right? So this is your isobutane chain, okay? Now if you go to see, the molecular formula is being fulfilled by both the structures, right? But there is a difference in these two structural formulas, of course. If you go to see, of course, the second methyl group, this methyl group is going to be attached on the second carbon atom, and this is your straight chain, fine? So in that case, if at all you go to take an example of the same base or the same parent alkane with some different functional group, that is, if you go to say it's going to be butyl alcohol, so you can have both the types in that case, that is N-butanol and isobutanol. So the structure will be something like this, wherein your OH group would be attached on the very first carbon atom in this case, and in the other case, the structure would be like this. Okay? So the chain differs in both the cases. Fine? Now, this was the explanation, or this was the molecular example for chain isomerism. Let us move on to position 1. Okay? In case of position isomerism, if you remember, the position of the functional group will be different. So in that case, you can take the example of one hexanol and 3 hexanol. Okay? So this is for the position isomerism. I'm going to draw the example over here. In both the cases, my structure, my molecular formula remains the same, but the structure is going to differ. So this will be the attachment of my OH group on the very first carbon atom, while in the second case, it will be on the third carbon atom. So my structure will look like this. Okay? So this is nothing but my functional group will be attached to different positions. Okay? In the very next case, we are having functional isomerism. Okay? Now over here, if you remember, we'll be having some different functional groups. Okay? So let us take an example of that of an aldehyde and a ketone. Okay? So in this case, I go to take propanal. Of course, you know what do you mean by the suffix al. It's the aldehyde. So of course, it is known as propanaldehyde. So it would be okay. And for a ketone with the same molecular formula, so please check out, the number of carbon atoms are the same, the number of hydrogen atoms, that is 3 plus 2, 5 plus 1, 6, and even in this case we are having 6. So it's C3H6O, but over here we are having a different functional group. Okay, so these are the functional isomers. Okay, now even if we take one more example of that of a carboxylic acid and an ester, so in that case you can have, say, propanoic acid. Okay, so let's draw the structure. Now, in case of an ester, of course, we know the functional group of ester is C double bond O dash O. Okay, so let us draw that first. Okay, and join it with another carbon atom. So let us fill up the other hydrogen atoms to get rid of the tetravalency part. Okay, so just count the number of hydrogen atoms. It is 3 plus 2, 5 plus 1, 6, 3 plus 3, 6. Okay, but the names are different, the functional groups are different. So if you go to write down the name for this one, it is nothing but dimethyl acetate. Dimethyl ester. Okay, so in this case I'm having the functional group of a carboxylic acid, while over here I have the ester functional group. Fine. So these are the functional isomers which we were talking about. Now coming down to something called as a ring chain. Now this is quite an interesting one, in which actually we have a very large difference. Okay, over here till now we were just playing with the open chain structures, but in case of ring chain isomerism, it would be a closed chain plus an open chain structure. So the very best example we can ever have is that of, you could say, again of 3 carbon atoms. Okay, so I take a molecule that is propene. Propene is nothing but presence of one double bond in a 3 carbon chain. Okay, so it's an open chain we are drawing. So that is something like this. We fill in the hydrogen atoms to get rid of the tetravalency. Okay, fine. And over here we draw a cyclic chain which actually gives us the same molecular formula. So this is something which makes up like C3H6. Okay, and the cyclic structure which gives me the same molecular formula is known by the name as cyclopropane. So just see, we are having an open chain structure and a cyclic structure. Fine. So this is nothing but this is a ring chain isomerism. So these two are ring chain isomers of each other. Fine. In the next part we will be seeing about metamerism and tautomerism. Okay, the very next branch of this particular category is metamerism. Okay, now if you remember, I have told you about this, that this is a very rare form of isomerism which exists. Okay, now this is actually limited to molecules which are having a divalent type of functional group. What do you mean by this is, let's take a specific example. Now if you go to speak about divalent, we of course know that such one are oxygen or rather ways sulfur contained functional groups. Okay, so in this case we can take the example of an ether functional group molecule. Okay, so in this case we can have a molecule such as this one. Okay, now over here if we go to see, of course the oxygen linkage is at the same position, right? Okay, now if I go to have a look at the metamerism or metamers, this will be perfect metamers of each other. What do you mean by this is, if I go to name this particular structure, This one is your CH3CH2 group, okay, that has been repeated twice and an ether linkage follows in. So this is your diethyl ether, while the other one is 1, 2, 3, that is methyl propyl ether. Fine. So this is the kind of metamerism which exists between these two different molecules, okay. Of course, it's the same functional group which is going to exist, but we'll be having some different arrangements in each of the cases, okay. Now, remember one thing, this is a very rare kind of isomerism which exists. It's just the different positions of the polyvalency functional groups, fine. Now, after this, we'll be having some kind of examples, some kind of good examples, which will actually make our concepts more and more firm in this topic of isomerism. Hello guys, today we are going to start with the most important topic in chemistry for this session. The topic is isomerism. Well, it does not form a whole chapter as such, but if we go to see, isomerism plays a very, very important role in predicting the group attached at a specific position in its structure, why it is going to be called as a product or why it is going to be called as a more stable form of that particular molecule. Now, before that, I need to tell you as to what do you mean by isomerism or what do you mean by an isomer. Isomerism is a phenomenon by which a molecule exists in its most stable state with the same molecular formula but a different structural formula. Well, stability of a particular molecule. What do you actually mean by it? Isomerism, if we go to define, is the phenomenon by which a particular molecule is going to exist in its most stable form. Lesser the energy of a particular molecule, more will be the stability. This is what we have been studying for quite a number of years. So let us see as to if at all a molecule is giving us a particular state of itself, that is with a particular functional group. Now, let us draw the structure of hexanol. You would be asking as to which hexanol are we drawing? Is it one hexanol? Is it two? Or is it three? It's going to differ as per the names. It is going to differ as to where is the OH group going to be attached. So let us draw the diagram or draw the structure. So here we go to draw. This comes down to the main term, that is isomers. Isomers are defined as the molecules, okay, two same molecules or either ways two different molecules wherein their molecular formula will be the same one. What do you mean by molecular formula? Exact condensed formula which gives us the number of carbon atoms, number of hydrogen atoms and number of any kind of heteroatom present in a particular structure. But they will be having some different structural formulas.